So let's go ahead and do some calculations here. Okay, let me go over what this example is. Again, this is the start of our calculation for industrial. Every building, industrial or otherwise, start with a transformer. When we deal with industrial buildings, guys, there are two types of transformers you can buy. Three-phase. Now we're talking about three-phase. You can buy a big fat three-phase transformer. That's one big box, primary, secondary, or especially in the industrial, you can buy three single barrels, three single transformers, and hook them up to give you a three-phase system. The reason why I picked this one for the industrial, because it could be common in an industrial, not common in commercial though. We don't do a whole lot of it in commercial, but in an industrial, we do a lot with it. Before I start, guys, this is your example number one. I want to make sure that everybody understands what we're looking at here. We're looking at, first of all, these are physical mechanical transformer. I have one big barrel, and a second and a third. Each one of them is 50 kW, single phase transformers. And I know you guys have done it with me and with Gary. Then we bank them together to make a three-phase system. Now, if you're an electrician, you know how to hook them up. Designers, we don't hook them up a whole lot, but when we hook them up, guys, when you have a single phase, as I said, these are single phase. Each one of these is single phase transformer. You have the primary always labeled H, the secondary always labeled X's. So H1, H2, X1, X2 for each one of these transformers. You can hook them up delta, delta, delta Y, 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 you name it. You can hook them up in any way. So the first example, we're going to do them. We're doing them delta on the primary, Y on the secondary. To make a Y, you take all the ones, tie all the ones together, and tie them to Mother Earth. You have to ground the neutral. Always, the neutral is always grounded. So we grounded the neutral, and we pulled my neutral. Everybody can see how they did the Y. You took one side of every transformer, almost always X1, and you tie them to Mother Earth here, and you tie them directly to N. That becomes the conductor for neutral. The three other phases will be from X2 of every transformer, phase A, phase B, phase C. That's the primary. The secondary. The primary side, we have H1, H2 all over. You take from a wire from H1 to H2, H1 to H2, H1 all the way to H2, and you take a conductor between every H1 and H2 to make a delta. So what they do is they put all the coils in series, and they take a wire between every two coils. Can you guys see that? Here's this coil. All the coils are in series, right? And then they took a wire and tie it between every two coils. That's how we make a delta. Any question about what we're doing? Three single-phase transformers banged to make a three-phase system. Not common in commercial, but it could be common in industrial. You get into industrial plant, you could have this transformer in your building. Advantage of this system is if one transformer craps on you, you can rewire as an open delta, and your building is up and running. Versus if it's a single box transformer, if one coil in the transformer is dead, you're dead. Okay, any question guys about this is how physically connected. The top is the graphic, the schematic of it. Here's a delta, here's a Y. My system is 480. I'm bringing 480 on this side. So the line to line voltage is 480. The coil, DC is coil. Everybody knows the difference between line to line. Line to line voltage is between the phases, phase A and phase B. Coil voltage is between right across the coil. This baby here is called the coil, right? We know that from the beginning. So this is the delta. On the other side, I have a Y. So the center of the Y is always grounded to both and neutral, and we get A, B, and C. Every system starts with a transformer. Okay, on the secondary, I decided to use 28120, and the impedance of this transformer, Z is the impedance, and it's 5%. The impedance of this transformer is 5%. Can I have a thumbs up that we know exactly what we're looking at here? Cool? Okay. So why do we start with the transformer? Because it all starts from the transformer. That's your valve. That utility brings the power into here, and they regulate how much power you can get inside your building by what size transformer they put outside for you. Okay. Before I move on, everybody knows that each one of these is 50 each, and we're banking them. They call it banked system. Bank them to make a three-phase system. Cool. You rarely would you see this one in a commercial building, industrial, common. Could be common. Utilities all the time, they do them. Okay, so that's basically the first, Before I move on, the most important thing is understand the system. Everybody understand what the system is? Delta Y, how it's hooked up together. And the red ones, guys, are fuses. So what do I need to do? Actually, I need to size the conductors coming into the system and the fuses on the primary, the conductors coming out of the system and the fuses in the secondary. That's what we do as designers. We design the conductors coming in, the conductors coming out, the fuses coming in, the fuses coming out, right? Okay, so let's go ahead and do that. The first thing, but to do that, I would like the first thing, guys, to start by just doing some calculation. The first thing I want you to find is something called banked kVA. A banked kVA is adding all these kVAs together. So I have 50K, remember that 50K kVA plus 50 kVA plus 50 kVA. That will, if you add all of them, they'll give you equivalent to 150 kVA. So who cares? These three transformers together make a system of 150 kVA capacity, three-phase capacity. Any question about that? Why 150? Just add them up. Because each one of them contributes 50. When you add them all up, it ends up with 150. Any question about that? Any question?
When you buy the transformer, once you know that it's going to be running a delta, for example, since the amount of current
you really can, yeah, you buy the transformer, you can hook up delta or Y, it doesn't matter.
All right, but if it's hooked up delta,
the current is going to be different.
3 times the current.
Yep.
Correct?
Yes.
Considerably more current than a Y through the coil of transformer.
When you buy the transformer, for the most part, hooking it up, I hate to say that, but for the most part, other than voltage, you really don't worry. Most of the time you have delta Y, most of the time. But you could go YY. And the only difference is the conductor will be bigger or smaller conductor when you size them.
I'm referring to the coil conductors.
The coil conductors.
Yeah. Don't they have to be, don't you have to have a larger one for a delta? If you're going to do it in delta?
Because of the size of the conductor? Well, the conductor...
Because you're running it through all, you're running the current.
Good point.
Through all 3 transformers.
The coils inside the transformer are rated to handle a delta connection or a Y connection. Very good point, though. Okay, so let's go, guys, for primary line voltage. Primary line voltage is, what's the primary line voltage? On the line voltage, that was piece of cake, that was 480. 480 volts, okay? Primary coil voltage, it's a delta. So what do you guys think the primary voltage equal V primary coil equal V primary line and also equal 480 volt. Piece of cake, this is a volt, okay? And I'm moving quick through these because it's easy. Secondary line voltage. What's the secondary line voltage? Secondary line voltage is 208 volt, piece of cake. How about secondary coil voltage? The secondary coil voltage is 120, right? Because it's 208, 120 system. So the secondary, everybody knows the coil voltage is line to line. I hope this is a quick review because we've done that. The secondary, the line voltage, the coil voltage right here is going to be right. This is V secondary coil across the coil, which is line to neutral, which is piece of cake. It's what is it? 120. Always 120 in this system. Any question, guys, about identifying the line voltage and the phase voltage? Now, tau, when we size things, you drop the word coil voltage, and we always use line current, line voltage. Always when we size transformer, when we size fuses and circuit breakers. Any question about identifying the voltages? But you need to be able to identify the voltage for a transformer. So we got that one. The second thing, guys, number 6 is a primary current, primary line current, and secondary line current. I put a star next to them here because these are the single most important thing you're going to do to size your fuses and conductors. The line current, not the coil current. Okay, so if you guys take the bank kVA, what was it, the bank kVA? It was 150K. Divide this one by 1.73, multiply it by the primary, it's 480. And if you do this one, and if you did this one right, you're going to end up with 180 amps. 180 amps. Any question, guys? Everybody knows how to find the amp for a transformer if it's 3-phase. You divide by the voltage, and because it's 3-phase, Chris, we use the multiplier for the three-phase, 1.73. Okay, secondary line current, the same thing. Secondary line current will take the same kVA divided by 1.73 times, what's the secondary line voltage? 208. And on the secondary side, that baby can pump 417 amp out of the system. 417 amp into the system. Any question about this? Now, William, could you please do me a favor, highlight the stars that I put here, because these two currents are the single most important currents for the transformer. Based on them, we size the fuses and the circuit breakers. The second two, primary coil and secondary current, I call it mental exercise for you guys, for the manufacturers really, but for us. Okay, so the primary coil current, because it's a delta, the current in a coil of a delta is usually, always take the line current divided by square root of 3, because the current will split. I don't know if you guys can see how the current here splits in a delta. In a delta, when you bring the current in here, what's happening to the current? It splits. That split is equivalent to the line divided by 1.73. In a Y though, the line current that's going through A is the same current that's coming out of the coil. Can you guys see that? So this goes one-way street. If it goes through here, where is it going to go through the same line? There's no fork. Everybody knows why in a Y, the line current and the coil current are the same. In a delta, the line current is 1.73 times the coil current, or the coil current equal the line current divided by 1.73. Okay, so let's go down quick here and size this is piece of cake, so the formula is always there. So I need the line current, which is 180. Divide this by 1.73, and if I did this math right, you end up with 104 amps. 104 amps. Same thing in a secondary coil current. Secondary coil is the same as the secondary line, so it's a 417 amps. 417 amps. And that's what Chris was saying. Here, the coil is going to see 417 because it's a Y, higher than if it was a delta. So they size the coils based on the worst scenario, worst current that the coil is going to see. But that's not for us though, for the manufacturers. Any question about these four currents? Which two currents are the most important for the transformer? The primary current. The primary current. Any questions about the primary current? Cool. Let me know when you're done. Okay, so we found the primary current and we identified the primary voltage. So they hire us not to do this. There's a couple of other things that's important, guys, that I thought also important to find, is the transformer ratio. Transformer ratio, they define it as V primary coil over V secondary coil, so coil to coil. So this one, it's going to be 480 divided by 120 coil to coil. And if you do that one, this equal 4. And to write this one in a ratio format, that will be a 4 to 1. That's how we write it in a ratio format. So this transformer ratio is 480 to 120, 4 to 1. 4 to 1. Transformation ratio is defined as voltage line over line. Transformer ratio, line over voltage, coil over coil. Transformation ratio is line over line. So you take a 480, divide it. What's the line on the secondary? 208. So if we do these two divided by each other, you're going to end up with 2.3. If you want to write them in ratio format, that will be, this is the ratio format. So every 2.3 volt on the primary is equivalent to 1 volt on the secondary. Line to line, line to line. In coil to coil, every 4 voltage in the coil of the primary is equivalent to 1 voltage in the coil of the secondary. On the coil of the secondary.
It's called transformer versus transformation.
Yes, transformer versus transformation. We use a lot the transformation ratio to give us the voltage, guys, and so forth. Okay. Any question about these two ratios?
Well, the reason of picking 124
Well, the coil to coil will give you, if you want to know, if you know the current on the coil current in the secondary, you can multiply by this ratio to find the coil current on the primary. If you want to find the line current, or if you know the line current on the secondary and you want to find the line current on the primary, you use this multiplier. So it helps you to find the current on the primary and the secondary, knowing the transformation ratios. As I said, you're going to be using this transformation ratio for all our calculations. Any question about this? Okay, so we need to go find the primary feeder. The primary feeder, guys, is always sized based on the primary feeder size is always based on the line. So what was the current on the line? 180 amps. 180 amps. You take this one to the lady who got married, table 310. Oops. We're going to take it. We're going to go size conductors, right? Immediately. So amps. Let's go here. 180 amps. Take this one to 310.15B16, the table based on 310, and you're going to go which column? 75, under column 75, right? Why 75? Because it's higher than 100. So you're going to go 75. What's the conductors and how many conductors do I need for this system? If you guys go there, you need the 3 aught, and how many conductors? 3 of them. Why 3? A, W, G, and what insulation do you need? Let's say it's inside. We're going to use T, H, H, M. That's it. So I need 3 conductors, 3 aught each, THHN. Why THHN? We're assuming it's in a dry location. Huh?
Not too cold.
And not too cold.
It'll break if it's cold.
Yeah, it's not a dry location. Secondary feeder. The secondary feeder, guys, is sized based on 417 amps. You use the line current on the secondary. Am I going too fast? Cool. Some of these are review too. So you take this one, you're going to go ahead and take it to which table? Table 310.15B16. We have been in this table many times, right? It's not new. Under which column? Always identify the column. And why? 75 degrees Celsius, right? For all of them Celsius. Why? Because it's higher than 100 amp. And then if you go there, how many conductors? How many conductors do you need? Well, I need at least three pairs. I have a neutral. Do I need to derate the neutral? You could derate the neutral at this time. Right now, I don't want to derate the neutral. You need at least, let me put it this way. So if you guys go there, you need a 600, the conductor is 600 kcm, okay? I need 3 conductors. Then the neutral, I can derate it. I'm not going to derate, I'm going to go full neutral this time. So how many conductors do I need? 4. What's the insulation? T, H, H, M. T, H, H, M. Any question, guys, about this? Any question about this? Does it make sense? We size the conductor on the primary, we're going to size the conductor on the secondary. Let me know when you're done. Secondary conductors. Okay, so this is warming up. Let's go. Are you good? All right, so let's go to number 14. 14 is the fuses. Now we size the conductors on the primary and the secondary. We need to go fuse them. We need to go fuse them, because you have to provide an overcapacity device. Now, Ashley, my friend, you're going to go to table. This is table 450.3b. We have been in this table, 450.3b. We're going to go to table 450.3b, and we're going to size our fuse. To size the fuse, guys, we use the full load amp, which is the line. Always, Rob, my friend, always use the line. When we size fuses and cables, we always use the line voltage and the line current. So what's the amp? 180. If you guys go to the table, it will tell you for fuses 450.3b, I'm going to have a primary and secondary protection. So let's go quick to this table. If you guys go to table 450.3b, very quick with me, I'm going to go directly, just flash that table. I know we've been there, so let's flash it one more time. Okay. Let's go all the way to the two tables that we're going to go. Should be somewhere here. There you go. Here's the two tables that we're going to be using. 450.3a, and the first one we're using is 450.3b. 450.3b, guys, is that baby right here. And I have primary, and I have my secondary, very important. So I have primary only protection, primary and secondary. I'm using primary and secondary protection because I have fuse on the primary and fuse on the secondary. Here's my multiplier because my amps are current. My primary current is more. Can you guys see the word more than 9 amps? So my multiplier on the primary is here. On the secondary side, current of 9 amps or more. So my current on the secondary is more than 9 amps. My multiplier is 125. Can you guys see note number 1 here? And if you read note number 1 here, it will tell you you can go to the next higher standard shall be permitted. Cool? Everybody knows how to use this table. So we have 450.3b. We have primary protection, secondary protection, and primary protection. We decided to use secondary and primary fuses, fusing on both sides. Common. Any question about this table? Cool. So when we go to this table, everybody knows which table are we talking about. So let's go add this one to my reservoir here and go back to where we were. Okay, so here's the table. Let's go. So we highlight this one. Everybody knows how to use that baby. And let's go directly into my fuses. All right, so let's go size the fuse. So what was the multiplier, guys, when we sized for the fuse number 14? We said our multiplier is 2.5. So I'm going to use this one here. So continue with the. So from here, you take 2.5 from the table, you multiply it by 180 amps, and that will give you a healthy 450 amp. Okay, so you take the 450 amp, you need to take it to 240.6. Everybody knows what 240.6 NEC, right? NEC 2011. 240.6, it will tell you the standard fuse is actually 450. So we hit the jackpot. And actually, if that was not a standard fuse, what do I need to do? Go down. Why down? Because if you guys remember, it doesn't say. If you look at the primary, here, does it have note number 3? The primary, nothing. You guys, I see note number 2. There is no note number 2. Number 1. Chad, make up your mind.
Is this circuit breakers and fuses?
If it doesn't say fuses, it's circuit breakers or fuses. Does it say, unless it specifies fuse, it's either one.
All right, so there are standard sizes for fuses.
Standard sizes, the table is both for fuses and circuit breakers. Non-adjustable circuit breakers. Okay, everybody knows why we didn't go, in this case, William, in this case, I don't have to go up or down. I hit the jackpot, so I don't have to go up or down. But if it was, say this was 420, you have to go to 400. Say this was 460, you have to go down to 450. Can I have thumbs up? We got it, Chad, move on. Yes, no? Phil? Good? 3 thumbs up at once? Oh my God. Okay, so if you go to the secondary, guys, the same table, you're going to be dealing with table 450.3b. On the secondary side, we're going to use, if you guys remember, on the secondary side, we're going to use number 15, I secondary line equal, that's the line that we'll be using, 417 amp, right? 417 amps. Then your multiplier is 1.25 from the table, 450.3b, multiply it by this 417, and that should give you a healthy 521 amps. And then you take your 521 amps, take it to 240.6 NEC, that doesn't sound even like a C. NEC 2011, and from here it will give you the next, you can go up, right? So the next standard is 600 amp is my standard, and if it's not a standard, what do you need to do? What can you do? Not need to do. What can you do? You can go up. I can't emphasize these arrows that goes up and down. This is so confusing, so please pay attention to when can you go up and when you go down. Dustin, the code allow me to go 600 amp. Can I put 500 amp? And anybody can answer. If the code allows you to go 600 amp, can you put less amps than the code allows you to? Yes. So what's the restriction in amps? The restriction in amps is you can't go higher fuse-wise and circuit breaker-wise, but you can go lower. One more here. If I am restricted to 450, can I go 400? Yup. But what are you risking when you put 400 instead of 450? You're risking that every time you energize the transformer, the circuit breaker or the fuse could blow up or trip on inrush of that transformer. So take full advantage, for the most part, unless you do coordination, take full advantage of the highest fuse that you can put. Unless you do coordination. We'll talk about this one later. Okay, any question guys about sizing the fuse? The last thing we need to size, I'm going to tell you why. Now, have I convinced you, guys, you've been with me almost for a year, have I convinced you that this is important to size a fuse or circuit breaker for transformers? That's what they pay us to do. The second important thing, short circuit. I emphasize this a lot in the industrial because now you guys will be doing short circuit analysis for me as we move forward. So when we size the short circuit, you take the short circuit is always on the secondary of the transformer, guys. If you want to calculate it for a transformer, you assume this is the assumption for this. And now I go a little bit deeper in this because you guys are a little bit higher here. So if you go to my transformer, here's the assumption, William. The assumption is there's an unlimited amount of current that Excel can pump into your building. That's the assumption. Unlimited. Unless you know otherwise, you have an unlimited amount of short circuit coming from Excel or any power company. The only restriction on how much current can go into your building is the valve, aka the transformer, that's holding that current from burning your building. So the only restriction is the valve, and the valve is activated by the impedance. The impedance of the transformers acts as a valve that protects the building, choke the current, does not allow all the current to go through. Okay, so that's the assumption. It makes a lot of sense, guys, when we start doing short circuit analysis. So what's the assumption? Excel can pump as much current into your building as you can. So this is how the available short circuit is based on unlimited amount of current coming into the transformer primary. Okay, then you take you take the secondary, always on the secondary, always on the secondary. What's the secondary current? The secondary current was 470 and divided. What was the impedance Z? 0.05. 5% is 0.05, and this will give you how much? 83.4 kVA. I want it in a kilo amp. 8.3. Okay, that's small amount here because it's secondary. 8.3. 8.3 km. This number is so important, because Dustin, my friend, when you size the circuit breakers that tie to the secondary of the transformer, when you size these circuit breakers, you need the interrupting rating of the circuit breakers to be as high as 8.3 or higher. 8.3 or higher. So knowing that the short circuit is 8.3, these circuit breakers most likely will be rated for 10 kiloamp. You can make them 25 if you want to, 220, but the higher the short circuit, what happened to the price of the circuit breakers? Higher. So optimum design, your circuit breaker that tied to the secondary of this transformer will be sized most likely 10 kiloamp. See why important this number is? As you guys go into the design, this is very important. It gives you an idea what size short circuit, what is the short circuit rating of the circuit breaker or the fuse, because I know what the secondary circuit breaker is, 600 amp, right? But when we size circuit breakers, three things we size them based on three things. Number one is the full load amp that you need to pull out of them, the highest amp. This case, you can pull a highest amp with 600 amp, non-continuous, and the interrupting rating, how much current they can interrupt without blowing up. I need them to be handle this amount, so that will be 10K. 10 is higher than this, so we're good. And the voltage. What's the voltage? The voltage in the secondary is 208, so I need my circuit breakers to be rated for 208 or higher. Most likely would be 300 or 600 volt rated circuit breakers. You're good to go. You see how important the short circuit and the full load? Any question, guys, about this? Any question? Yes, sir.
I got 0.02 D1.
And you took 417 and you divided by 0.05? Anybody else get that? Then you divide by 1,000, of course. I had 8.3. Anybody else? Your calculator need brain. Who's the brain surgery here? Sorry, Dustin. Anybody else came up with a different number? Majority rules. Your calculator need brain surgery. 8.3K. Any question? All right, let's take another example. Very quick example. Now that you guys are up and running. Here's example number 2. Any question, guys, about example number 1 before we move into example number 2, please? Any question? Yes, sir. The first page? Okay, let's go back to the first page. Here's the first page. The second page, okay. Second slide. What's your question? Getting rough around the edges these days. Allah. It was, serious? Isn't that amazing that how the calculator is garbage in, garbage out sometimes? If you push the wrong button, computer is even worse. Any question, guys? Okay, so I'm going to go quick and move to another example for you, and then we'll give you the homework at the end. Okay, Aladipo, good. Thank you. Anybody else before I move to example number 2? Okay, here's example number 2. Example number 2, guys, we have a transformer, the same transformer now, the same transformer, except same transformer. I didn't do the physical. Each one of these transformers is 750 kVA, 750 kVA. The impedance is 6. The primary current, Chris, is 13.8. The secondary current is 480-277. And we need to do the same steps for this transformer. Same steps. We're going to calculate the same thing. Cool? And then you guys are going to do one more for homework, then you're good to go. Okay, any question about the inputs? We have a transformer, the same thing, delta Y. The only difference is the voltages are different now. Look at the primary. I have a medium voltage primary and a low voltage secondary, 480. And the impedance is different and the size of the kVA is different. Okay? All right, let's go ahead and start. Can I have a thumbs up? Yep, Chad, we understand what the system is and we need to size. Okay, cool. banked, they call them banked kVA. Banked kVA, basically adding all the kVA of the single phase transformers. So how many of them do I have? I have 3. So I have 3 times 750 kVA, and that will give you a healthy 225 kVA. Piece of cake. So my banked kVA, everybody knows what a banked kVA is? That's how much kVA 3-phase wise that you have in your system. So basically, William, you can go throw these 3 transformers out the window and buy yourself a 3-phase transformer equivalent to 225 kVA, and the calculation will continue to be the same. Cool? We banked them 225 kVA. All right, so we're going to do the same thing, and I'm going to go fast on this one. The primary line voltage, piece of cake, guys, is 13.8 kVA. Everybody knows what 13,800 volt. 13, it's a high voltage, 13,800 volt. V primary coil is the same thing, 13,800 kV. So these are the primary, because why? Jackson, because it's a delta, right? Let's go directly into the V secondary. V secondary line is 480, just by looking at it. And V secondary coil, as the coil is the line to neutral. The coil voltage is the line to neutral. What's the line to neutral? V secondary coil is 277 volt. You should be able to identify these voltages on the primary side and the secondary side of this transformer. Any question? Piece of cake. Up to this point, piece of cake. Any question? These are piece of cake. There's no calculation, just identifying the system. Identifying the components of the system. Any question? Okay, can I move to the next one? Yeah. All right. Now, I put that little asterisk here or star to identify that 6 and 7 are very important quantities that we're going to use to size things. So I primary line, the primary line, guys, piece of cake, Chad, we're going to take 225 K, remember the K, divided by 1.73 times, what's the primary voltage? 13.8 K. And oh, by the way, the K goes with the K when you do your calculation, right? You guys know how to do the math, right? If there's 1,000 at the bottom and 1,000 at the top of a division, what do? They cross each other, so you don't have to do the calculation. And then it becomes 225 divided by 1.73 times 13.8. And if you do that, you're going to end up, if I did my math right, you're going to end up with 9.4 amps. 9.4 amps. 9.4 amps, Chad? Are you kidding me? Not less than a 15 amp circuit breaker? But look at the voltage. Can you guys see what the voltage is? The voltage is what? Huge voltage. That's the advantage of using medium and high voltage. You can pump up the voltage and the current will go way down to ground. Who cares? By increasing the voltage, guys, we lower the current, which means you can carry smaller conductors. All these power lines will be carrying smaller conductors because the voltage is high. Any question? Okay, so this is I primary line. Let's do I secondary line. I secondary line is the same thing, 225 kVA, 1.73 times 480, because the voltage on the secondary is 480, right? We're on the secondary side. That would be equivalent to 271 amps. 271 amps. 271 amps. Now, I primary coil, piece of cake, I primary coil equal I primary line divided by 1.73, and that would be 9.4 divided by 1.73, and that will get you a piece, a tiny little 5.4 amps. On the primary, on the secondary, I secondary coil equal I secondary line and equal 271 amps, done deal. Any question? The most important two currents are 6 and 7. Line primary and line primary and line secondary. Any question guys about this? Everybody knows why I divided by 1.73 the line, because it's a coil in a delta. It's blitz. Cool. Jackson, makes sense? Okay, let's go find the transformer ratio. Transformer ratio. Number 10. Did I miss anything on the number? No, number. Okay. Okay, so what did we do here? I secondary. Okay. Transformer. Number 10, transformer ratio, guys. You're going to take the 13.8. Let me see. There you go. When you take 13.8 K, don't forget the K, divided by 277, that will get you a healthy 50, and that will translate to 50 to 1. 50 to 1 transformer ratio. Transformation is line to line, so you take the 13.8 K divided by 480. That will get you 29 for the most part, 29, and that will translate to 29 to 1. So that translates to 29. Who cares? This means on the primary, I have for every voltage on the secondary, I have 29 voltage on the primary line to line. For every voltage on the secondary, 1 voltage in the secondary, I have 50 voltage on the primary coil, on the primary coil. So see the coil to coil, comparing coil to coil versus line to line. You can use any one of them. As I said, the most important transformation ratio will get you the ratio that you need to do. Okay. Any question? We got the transformer ratio. Now, we're dealing a couple of things, guys. Primary feeder size. Primary feeder size, Ashley, my friend, now we're dealing with high voltage conductors. The high voltage conductors are rated 5 kV, 15 kV, 35 kV, and higher. Now we're not dealing with 600 volt THR conductors. We're dealing with higher. So what I did, guys, I listed a couple of voltages commonly used in the US that we use at, if you have a feeder that's rated, if you buy a medium voltage conductor, it's rated for 5 kVA, you can use it for 4160, or you can use it for 2400, right here. If you have a feeder that's rated for 15 kV, this can commonly used in the US for 13.8 and 12.47. They call them 13.8 and 12.47, and there's also 13.2, I believe. If you're using a 35K feeder, this is commonly used for 22K and 33K. Anyway, these are medium voltage systems. Most of you guys, unless you work for utilities, most of you, you probably have stopped at the 15 kV. Most of you at 15 kV, bring a feeder to the building at 15 kV. That's 15,000 volt, the cable. Remember, up to this point, I know we did one example last year. Up to this point, we were just dealing with what? With 600 volt or less. Now we're moving to a bigger cable. Okay, Who cares? When we move to a bigger cable, we have different tables that we have to adhere to. Different tables that we have to adhere to. So when I size the primary, I have to go to the line, like we've done all the past, and I have a 9.4 amps. Now I bet you William is saying, Chad, I can carry this with number 14. Hold your horses. Had this load been 600 volt or less, number 14 is good enough for you, right? But remember, the voltage that this cable is carrying is 18,000 volts. So your cable has to be 13.8 thousand volt, or 13.8 thousand volt, 13.8 kilovolt, which is 15 kVA feeder. So to do this, we need to go to the following table, my friends. The table that we need to go, they changed in 2011, so I'm going to go grab it, grab the new name, and let's go directly into 310. What we used in the past, we used 77. Okay, here you go. 310.60C77. This is table 310.60C77. NEC 2011. If you go to 310.60C77, you're going to find, let me just put the numbers and then we'll go there and look at it. You're going to find the size that you're going to do is 3 conductors. Why 3 conductors, by the way? Why 3 conductors? 3 phase. The minimum size that you can use at this voltage is number 6. And the insulation, it's called medium voltage dash 90. Tau, this MV-90, this is equivalent to your THHN or THHW. Okay? I'm going to go, guys, quick flash this cable when you're done writing it and show you how we came up with this number. Okay, flash this cable and show you how we came up with this number. So 3 conductors, different table. Okay, so let's go directly into the NEC Code Book, and let's go into okay, so let's make a detour here and all the way to 310.16. I always go for the bottom because it's easier to come to it from here. So we're going to go all the way to 310.6077. Here you go, 310.6077. These are, guys, 80 all the way. 77, did they say? 77. Here you go. These tables, 310.60 is the article that talks about medium voltage cables. Anything higher than 600 volts, you're going to be defaulted to Article 360. 360 refer you to this table. Let me just flash this table and say very few things about it. So,
Article 310.60?
310.60. 310.60. 310.60, if you guys go there, look at this. This will give you the following. First of all, it will give you that basically 3 single insulated copper conductor in underground electrical ducts, 3 conductors per electrical duct, based on an ambient temperature of this 20, and the electrical ducts arrangement based on 310.60 and the percentage load and so forth. All what you need to understand is, what was the voltage level that we have? You guys remember the voltage level that we had? We have, so we, based on detail, we're going to be using medium voltage 13.8. We have 13.8 and we're using 90, and the smallest conductor that we can use is what number? Can you guys see at this voltage? What's the smallest conductor that we can use? Number 6. Okay, now when you deal with these tables, guys, there's detail. Can you guys see detail 1, detail 2, and detail 3? Detail 1 is actually one big duct conduit inside the 3 medium voltage conductors. That's what detail 1 is. So let's go quick to detail 1 before we even size it. If I go, here you go. Can you guys see these? These are the details. Here's detail 1. Can you guys see detail 1? Detail 1 that we're using is basically this detail. This is a big conduit with 3 medium voltage cables inside it. Medium voltage cables. Okay? Why did I use detail 1? Because detail, how many cables do I have? 3 cables. I can put them in one big conduit, and that's detail 1 would work good for me. Everybody knows why detail 1. If I parallel 3 phases, I can put them detail to circuit 1, circuit 2, circuit 3. If I parallel 6 circuits, so imagine a system that you guys have to pull 3 circuits, 3 3-phase circuits. So you can use this detail, or you can pull 2 circuits, 1 conductor in each set. So for the time being, without getting too deep, we only have 1 circuit, meaning 1 phase A, phase B, phase 3, and I will use this detail. Most of you guys, unless you do higher system, you're almost always going to be in this detail, or this detail, or any of the combination here. So this is the most common one, probably. You end up pulling them in 1 conductor, unless they're too big to be pulled in 1 conduit. Then, if the circuit, guys, take this. If I have 3 conductors, medium voltage, and they're so huge, as in 100 kVA, 1000 kVA, or higher. I have 1000 kVA. Pulling 3 conductors, 1000 kVA in 1 duct is a nightmare. You can't do it. So you know what they do? They pull them, each cable goes in 1 duct. That's where you can use detail number 2. Or 1 application.
There's actually 3 conductors.
This duct could be 3 single conductors, could be 3 single conductor cable, or 3 conductor, 1 cable, 3 conductors inside it. Each one of these dots. Okay, so we take this one, snapshot it. And let me just go back. So this is the detail, we say detail 1. Let's go, guys, directly into 2000, what did we say? 277. Why 277 the most common? Here you go. So right in here, this is where I want to flash it. So we decided to use copper because Chad loves copper. And we decided to use 3 single insulated copper conductors, 3 single insulated copper conductors in an underground duct, right? So all these, and we're using detail number 1, and everybody knows why detail number 1. And the voltage that we have is 13.8. So actually that will put us right in here because my voltage is 13.8. And single-handedly, you can have 2 cables. You can buy 2 cables. One is rated for 90 or one is rated for 105. Commonly used 90, so I'm going to default to 90. Can I use 105? Yep, you can. Commonly we use 90. And then, what was the amp that I'm looking for? I was looking for 9.4 amps. So go down all the way. The smallest amp you can start counting is 90. That will cross-reference this baby with which number? Number 6. Any question? Now, on the test, William, what I'm going to give you, if I give you, the system is 4160, 4160. Which set of columns are going to be defaulted to? Right here. So really, most of the time, you are either in this column or that column. Yes, Chris?
You don't use the fuse size to
No.
select your cable?
No. Otherwise, you oversize. Any question, guys, about this? Everybody knows why we use this one. Now, the one next to it is if you are cheap like Chris, you're going to buy aluminum. Then you go right here. It's the same one. It's just for aluminum cables. And the rest of them, guys, different details for different cables and so forth. All these tables, I'm going to emphasize the first one here that we can use. Any question about this table? Because I know we flashed it one time last quarter. And that's emphasizing why did we use this table. Okay, we got out of here and go back to my presentation. Here's my table up here and go back to where we are. Okay, we got these voltages, we got these, we got these. All right, so did we size the primary? I think we were, where was the size of the primary? Here you go, the last one. There you go. Any question about why we came up with this size, please? Any question about why we came up with this size? 3 conductors, number 6, MV-90. I'm going to say here detail number 1, just to get you an idea which detail we use. Detail number 1. Detail number 1. Okay, any question? Because that's new then kind of a little bit level. Okay, can I move to the next one? Cool, everybody knows how to use this table? All right, so here's the tables. Keep going. All right, so let's go to the secondary conductors. Secondary conductors are a piece of cake. They're 480. So Chad, that's what familiar with that. So not a big deal. So if you guys go to number 13 is going to be secondary conductors. I have 271 amps. 271 amps. And if you go to table 310.15 B16, and this is NEC 2011. And which column are you going to go under? Always 75 from now on. This will get you how many conductors and why? This will get you 300 kcm. Now minimum, I need 3 conductors for the 3-phase. And I need also a neutral. I can derate the neutral, but for this exercise, I'm going to pull full neutral. So how many conductors I'm going to pull? 4 conductors. What insulation? Let's just use 2THHN. Any question? So typical. This is we size them like we did before. 300 kcm. HHN. We're going to go size fuses. For fuses, guys, I'm going to go flash one more time the code. We're going to go flash the code. We're going to go back into article. Which article were we in? The article that talks about transformers. I want to go from the back. Well, let's go here. So actually, you don't have to go from the back. Here's the transformer article. I'm going to go to table. This is table 450.3a. 450.3a, the one that we're going to size the fuses, guys. 450.3a. The most important thing about this table is you use it if you have anything higher than 600 volt, primary or the secondary. Remember B? We use B if the primary and the secondary were both 600 volt or less, both of them. If one of them is higher than 600 volt, you have to go to A. 450.3a. 450.3a. I don't know if you can see that one. 450.3a right in here, and it says over any one side over 600. Okay, so how are we going to size it? The first thing I would like you guys to look at is the primary. Is my primary, here's my primary. Is my primary over 600 volt? Yup, my primary is over 600 volt. Am I using a fuse or a circuit breaker? What did I use here? We use the fuse. We use a fuse. Commonly used is a fuse, so I decided to use a fuse. Okay. Your default is going to be any location. My default is any location here. Is my default unless I know otherwise, supervised and so forth. And do I have not more than so fuses any location, right? So not more than 6. What was the impedance of this system? 6. So am I under not more than 6? Right? I'm here. So this location, and I'm also here because the impedance. Can you guys see the impedance is 6, not more than 6? So what's my default? 300. Can you see note number 1? Yeah. What does note number 1 say? Say if you hit the next stand, if you don't hit the standard, go to the next standard. Right? Can you guys see that? Everybody can see that? On the primary side. That's the primary side. Everybody knows why we went to the primary side this way? Any question about the primary side? Default fuse. Can I use a circuit breaker? Yes. Why do I use a fuse versus circuit breaker? Fuse is on the high voltage cheaper. Okay, if I use a circuit breaker, Ashley, what's my multiplier for this? 600 volt, right? Okay, let's go to the secondary side as long as we're on it. Here's my secondary side. Is my secondary over 600? No, God forbid, it's less than 600, perfect. Am I using a circuit breaker? What did I decide to use? I decided also to use a fuse. Well, it doesn't matter here. If it's less than 600, it's a fuse or circuit breaker. It really doesn't matter. And what's my multiplier for this is 125. Do I have note number 1? Yep, I do have note number 1. So on both sides, if I hit a non-standard, where am I going to go? Up. Both sides, if I hit a non-standard, where am I going to go? Up. Any question, guys? Everybody highlighted these areas? in the NEC Code Book? What I'm showing you is a typical design. Typical design. Now, William, if your voltage on the secondary is over 600 volt, which it's not, then you're going to go to this column. Chris, can you see when you go over 600 voltage, they start to separate the fuse from a circuit breaker, because the price becomes big deal and the size becomes big deal and so forth. Can you see the multiplier here? It's not a big deal, but here look at the difference: 600 versus 300, double. It's misleading though here. Any question? Everybody got that one? So let's go take a snapshot of this baby and go back to where we were.
Circuit breakers more expensive than fuses.
Yes.
They let you run that up to 600%. So you're really okay on that.
That's why I say it's really misleading, because at this level, you size by relays. You buy, they don't even make less than 600 amp medium voltage. You don't even make them. So you start by a big circuit breaker and you size them with the relay, tweak them with the relay. So really, it's not like you can buy a 15 amp, a medium voltage circuit breaker. You start talking about 600, 1,000 amp, and then you start reducing them. So they're very adjustable. Okay, so let's go, guys, back quick here to the fuses. Now that we know what the fuses are, I'm going to go directly and write my fuse on the primary. On the primary side, my fuse on the primary, can you see the number one that says go up? What was the multiplier? 3. So I'm going to take let's use red here because it's a different color. So I have 3 multiplied by the I primary line, and this will be 3 times the I primary line was 9.4, and if you guys do that one, you're going to end up with 28 amps, not a whole lot. Then you're going to take the 28 amps, take it to table 240.6 under 240.6 NEC 2011, and that will get you a 30 amp fuse, at 15,000 volt. I can't emphasize 30 amp fuse, but look at the voltage though, at 15,000 volt. This is not a fuse that you can stick there. That's a big boy, 15 amp fuse. Why did they go up, guys? Yeah, I have to put my up sign always. Why did they go up? Because I have note number 1 that says, oh, by the way, if you did not hit the jackpot, please go up. Why did I go up? Because note number 1 tells me go up right in the table. And if you don't believe me, because you guys are doubting Thomas, oops, not here. Like, so can you guys see where it says note number 1 right here? It takes you down here, it says, oh, go up. All right, cool. Let's go, almost there. I know you guys are hungry, and me too. Okay, so same thing, guys, for the bottom one. On the secondary side, though, the secondary side is piece of cake. You're going to take the secondary side. We're going to take 1.25 multiplied by I secondary line. 1.25 times, what was the I secondary line? 271, and that will get me a healthy 339 amps. 339 amps. Up to this point, we can custom design ourselves 339 amps, or take advantage of the code and go to 240.6 NEC 2011, and that will get me what's the and by the way, if it's not a standard, it also has a note number 1 that you can go up. I like these color stuff. Go up. So what's the next standard? 350?
Yes.
350. So a 350 amp. My next standard is 350. My question for Jackson, my friend, can I use 300? Yes. Can I use 200? Yes. If you go lower, what's the advantage of going lower? More protection. What's the disadvantage of going lower? You're taking a chance that the fuses will blow blow up on inrush when you start the equipment. Almost there. Any question, guys, about this? Can anybody tell me what's the voltage of this fuse? 350? What's the voltage of this fuse? Huh? 600. The voltage of this fuse, 600. I didn't write the voltage next to it because if you're low voltage, most likely you're 600 or 300. In this case, we're 480, so we're 600. This one is the typically you write the voltage next to it because it's higher than 600. Any question? Okay, let's go to the last one. Oops, not here, not here. Okay, the short circuit. The last one, guys, is short circuit. The short circuit is always on the secondary, not the primary. You can't calculate the short circuit in the primary. You have to contact the utility to get you that number. Always on the secondary. So on the short circuit was, the secondary was 271, 0.06 because the impedance was 6%. And do I come up with 4.5 or 45? 4.5 kL. Always use K when you do short circuit. Don't talk amps. When you do short circuit, guys, the language that the industry use is the kiloamp. When you do full load, it's amps. Interrupting rating is always kiloamps. Okay? Okay, the last thing is our homework. Our homework is going to be an impedance of 2%. Here's the homework that you guys need to do. Homework number 1, please mark it. Homework number 1, I have a transformer. It's 4160 on the primary. On the secondary, 28120. The kVA of the transformer, everything together, the kVA of the transformer is 100 kVA, pure transformer. So how many of them do I have? How many transformers do I have here? 3. So I have 100 kVA pure transformer. They're single phase. There are 3 of them. There's 1, 2 per transformer. Thank you. Per transformer. So here's 1, there's 2, and there's 3. 3 single phase transformers banked together to give you a 3-phase system. The impedance of this system is 2%. What do you need to do? I want you guys to calculate the 16 things that we did. 16 things. So you're going to do, what's the outcome? What do I need to do? What I need you guys to do is calculate item 1 through 16. Was it 16? Yeah, through 16. You give it to me whenever you're done with it. Basically, you're going to follow one example. This one actually goes with example number 2 that I gave you. Everybody got the homework? That's how I'm going to do the homeworks from now on for this, guys. We'll do 2 examples similar, and then at the end I give you a homework so you can exercise with it. Hopefully 2 examples of homework will get you there. That's all we have for today. Any question? I wanted to do another example about transformers, guys. We'll do it tomorrow, plus generators and other things. Thank you.